So we've talked a lot about generating electricity. Now we've seen that the variation in the rate at which that energy is generated, namely the power delivered, fluctuates, and we have to find a way of stabilizing the delivered power to the consumer. And to do that, we turn to the question of energy storage. And this turns out to be an extremely important research area, as we will soon see. Now, the major energy storage methods include hydroelectric, and we don't think necessarily of hydroelectric as a storage technique because typically the large dams that drive the turbines that create electricity from the flow of a river, they're run day in, day out. But when you shift to renewable energy, wind, solar thermal, photovoltaics and so on, with a fluctuation, it's very important that hydroelectric power be brought to bear on this problem, because you can release water through the turbines on a dam very, very quickly to compensate for a drop in the input from wind or photovoltaics. The next aspect involves electric vehicle energy storage, and this is a little counterintuitive. And it also depends on the total number of electric cars that are owned, because if you plug your electric car into the wall socket, you can do two things. You can either charge the car, and when it's fully charged, it'll stop drawing power, or you can program that electric vehicle to purchase electricity at the inexpensive point, that is at night, and sell the electricity back to the grid under high demand cases. And when you analyze the input of electric vehicles into the fraction of vehicles that are used, it turns out that when electric vehicles reach 30–40% of the total number of vehicles, this is an extremely important, highly flexible storage method for energy. Then thermal energy. This is another very simple way of storing energy. For example, if you have a large block of ice in your backyard and you live in a low latitude, you can purchase energy to produce ice at a low cost, namely at night, and then draw off of that thermal energy storage to cool a house during the day. And equally true, you can use a very high temperature block submerged in your backyard, and you can heat that with electrical power when electrical power is cheap, and then draw off of that high temperature thermal to heat your house. And it saves a remarkable amount of both energy and resources. Pumped water storage. You can pump water uphill. It's the opposite of hydroelectric power. You can pump water uphill when it's inexpensive and draw off of it by draining that water through a turbine to recapture that energy. Biofuel and waste incineration. These are two very important components, as is quite surprisingly compressed air storage. And this is a technique wherein you use electricity to increase the pressure in an underground cave. It sounds a little far-fetched, but it actually works very, very well. Those caves are absolutely sealed, and you can increase the pressure, and when you need to withdraw that electrical energy, the pressure on the inside drives turbines the same way water would, and you can recollect that energy. And then finally, a major area of research is flow batteries. Flow batteries use huge tanks of chemicals released into the anode or cathode or both of an electrical battery system. And the big advantage of flow batteries is that they can contain a massive amount of energy. And of course, when that battery is recharged, the chemicals cycle back in the opposite direction, as we will see in the electrochemistry chapter. We're interested in quantitatively analyzing the ability of each one of these to bridge over these large gaps that are created by the absence of both wind and solar power, for example. And to do this, we want to analyze the ability of each one of these storage techniques to give us the amount of energy required to cover the worst possible case